Hello, everyone, and welcome to today's session on performance. This is the second time we've run a performance webinar. We didn't learn our lesson from the first time. So today we're going to be bringing you a bunch of fresh performance-related information to CockroachDB. Today, I'm joined by the ever wonderful Glenn Fawcett, who's joining me from the West Coast. Thank you for joining, Glenn.
You're welcome. Yeah, it's always fun to get together and talk about my favorite subject, performance optimization. Anyway. Yeah.
So I'm Rob Reid, technical evangelist here at Cockroach Labs, and Glenn is our principal services consultant with a specialization in performance. Glenn, do you want to tell our audience a little bit about what you do?
Yeah. Well, actually, it goes back to most of my career, whether I wanted to or not. I started off focusing on performance. Back in the days when I worked at Sun Microsystems and Oracle, doing TPCC performance work. But about 6 years ago, I'm just coming up my 6-year mark at Cockroach. I joined Cockroach Labs because I could see a new focus on how to bring databases out in the world in a more distributed fashion. So what I do is I work with now at Cockroach at the most pivotal customer accounts as a consultant, and also to help really kind of a partner to partner with our largest customers so they can achieve the best performance. And part of that effort actually allows me to then feed back some of the learnings that we have from various customers, because I tell you, engineers can test things, but customers find the most interesting problems that we can feed back and make the product better for everyone. So that's my focus.
We do indeed. We do indeed. I can say that because I've been a customer of Cockroach Labs.
Yeah.
So yes, today everyone will be talking about the importance of database performance. We'll be exploring CockroachDB's latest performance developments. We'll be sharing performance best practices, and we'll also be sharing some experiences of customer workloads, real-world workloads, and their performance journeys. As with all of our webinars, if you have any questions at any time, the best time to ask them is when you have the question. So pop the questions in the Q&A channel and we'll get to them as quickly as we can. And there'll be a survey at the end. If you could take some time to fill out that survey, that would be really appreciated because it will help us make the next webinars better. Without further ado, let's go into why performance matters. This slide is similar to one we used in our previous webinar almost exactly a year ago now, but we wanted to keep it in because it sets the stage so nicely. So the 100 millisecond rule, while maybe not on paper, it's an unspoken rule, says that anything that's less than 100 milliseconds is typically imperceptible to a user, whereas anything that's 1 second or more is perhaps just about acceptable, but over 2 seconds becomes an annoyance to the customer. And that impacts user retention. If your website or application is annoying to use, customers will find another application to use. The new part of this slide is around distributed SQL specifically. A traditional monolithic or legacy database assumes that there's a co-location of everything, CPU, storage, on one node. So you're looking at a different kind of latency profile than you would to a distributed SQL profile. Not only are there multiple nodes involved in a distributed SQL database, but those nodes might be geographically dispersed. So Glenn and I ran this almost exactly a year ago, and we've got a lot of new and exciting features, some of which have performance benefits. We'll talk about those in these next slides. We have our first question. The session, oh, someone is typing. So thank you, Alicia, is working hard in the background to answer those questions. Thank you. So the first entry in our new release list is the CockroachDB standard tier, which is a bridge between our existing basic and advanced tiers. It offers customers who need provisioned capacity the guarantees that they might require in terms of throughput per second, etc., but they might not require the dedicated hardware that advanced provides. So it sits somewhere in the middle, and it comes with a bunch of features, security features and otherwise, that aren't available in the basic package. And standard, as an aside, provides a compelling price performance cost efficiency over dedicated hardware, which we'll explore now. So let's look at a typical business day across 3 time zones. The database icons above the map represent the database regions. Remember, this is all happening in one logical distributed database. And at their busiest, the US region on the left will consume, let's say, an arbitrary amount of 6 vCPUs, while in Europe, it will require a maximum of 4 vCPUs, and Asia Pacific will require a maximum of 2 vCPUs. Just for this example, the global workload is unbalanced. On this slide, the table on the right shows the region, the database region, the local time in that region, and the current number of virtual CPUs that workload requires in that region at that time. So let's assume at the moment that it's 4 p.m. in Asia Pacific, and they require this. So this is their busiest period, and it requires the maximum of 2 vCPUs for that region. While in the UK, or I always go back to default to UK, I'm sorry, the EU, they're just starting to come online on their business day. So they're requiring about half of the CPUs that they would require at max. And the US is currently offline at 3 a.m. You'd hope they're offline at 3 a.m. requiring 0 CPUs. So a total CPU utilization of 4 vCPUs across the global cluster. Fast forward 8 hours and the situation looks quite different. At its busiest, the US is now online at 11 a.m., requires 6 of the total 6 vCPUs for the busiest period of their day. The EU, right at the end of their busiest period, requires 4 out of 4 vCPUs, and Asia Pacific at midnight is currently requiring 0. The total vCPUs at this point of the day, which is about 3 o'clock UTC, is 10 vCPUs. Fast forward a further 5 hours, the US is coming to the end of its day, but it's still at the busiest period, 6 out of 6 vCPUs, whereas the EU and Asia Pacific are currently offline at 9 and 5 a.m. respectively, requiring 0 CPUs, a total of 6 vCPUs. So looking at 7 a.m. when Singapore was online, but none of the other regions were particularly busy, we required 4. Then at 3 o'clock UTC, we required 10. Before 8 UTC, 6 vCPUs. The busiest period of time in that 24-hour period was at around 3 o'clock UTC in the afternoon. Most virtual CPUs were required at this time. So that's the amount of vCPUs you would want to provision for your standard cluster. And we always recommend budgeting around 40% above that to give yourself some headroom to account for unexpected spikes in busyness. So let's move on a little bit here. And this is what it might look like on dedicated hardware. Not forgetting the 40% headroom that you would be recommended to apply. If we are running the same workload as before on dedicated hardware, the smallest virtual CPU configuration you might require would be 18 virtual CPUs. If we take the 6 vCPUs required for the US, add 40% and round up, we've got 9 vCPUs, 6 in Europe and 3 in Asia Pacific. That is an unbalanced workload and it would require 18 vCPUs. We wouldn't recommend running such an unbalanced workload. This is quite an extreme example, but if the US region were to fail, for example, there wouldn't be enough capacity in Europe or Asia Pacific to take over that workload or even to replicate amongst them for global tables. Whereas a balanced workload where you have the same number of CPUs in a node, for example, across each is a much better, safer way to run a cluster, but it would require more vCPUs. Remembering back to our standard cluster, which could satisfy the same workload with probably about 16 vCPUs, adding the 40% headroom. Now, we were thinking of doing a demo towards the end of this session, but I don't think we're going to have time to do that. There is a link. We'll share a link as well in the chat, and it will be available in the link to our webinar on asymmetric workloads. So if you want to take a couple of seconds to scan this QR code, that will take you to a YouTube video whereby I perform exactly the same thing that I would have performed had we had time today. So the next performance improvement I'd like to talk about in CockroachDB is columnar block format. And this is a change to the way we physically store data on disk in the key value layer. In a row-based system, each row in the file corresponds to a logical row in the database. Contrast that to a column-based format where each row in the file represents a column and a number of rows for the column it allows us to achieve some performance improvements. So block level performance here is referring to specifically the SST file read from disk, obviously not the end-to-end, including networking involved in a request. So in short, it offers better performance at around equivalent amount of disk space used. The next improvement is admission control on writes. Prior to CockroachDB, so I think from 22.1, we introduced admission control, and it protected foreground workloads from endogenous or internal stresses, things like CDC, change data capture, or backup and restore operations, things that might stress a foreground workload. We protected so that they wouldn't impact the foreground workloads. But as of 25.1, we can now protect foreground workloads from themselves. So it works in a kind of token bucket sense, such that in busy periods, the bucket would fill up and then drain to allow a consistent level of write throughput to the cluster. We have another question, and yes, we can share the slides at the end, or it might be part of the recording. I'll let Alicia answer that one, if that's okay, Alicia. The next thing is disallow full table scans. That's existed in the product for some time. It went into the product in 24.3, but as of 25.1, there's a new default for the large full table scan rows setting that accompanies this. So if you enabled the disallow full table scans in 24.3 or anything up to 25.1, it would set a default value for large full table scans to 1000. So essentially, you would still run a full table scan if the table was 999 rows or fewer. As of 25.1, the new default value is 0. So when you disallow full table scans, you are doing just that. You're disallowing full table scans, unless you change the value for large full scan rows. Glenn, what is your... We've come to the end of our recent performance developments. Do you have a favorite performance update? And are there any I've missed?
Well, actually, I first put a comment on this one. That this can be very useful if you think about it. Allowing, I mean, full scans in general are something you want to avoid. Typically, it means you don't have the right indexing, or the stats are off on your queries that will cause you to do a full scan. But this is nice to be able to kind of put a safeguard in place for the customer, but still allowing for some of these large full scans. I've used this quite a bit because you might have a lookup style table that you have, and it's fine if all the rows, if you have 1,000 rows or 100 rows that are in a lookup table, a full scan is actually the best way to get at it, to be quite honest, because it's just one single little lookup. So there's that. The other things I like that have been introduced in recent times are the ability to do generic plans. You do prepared statements and generic plans. They tend to be a lot more efficient because we can pin down the actual execution plan. So that ends up being you have less offs basically when the optimizer will pick up wrong plans. So that tends to be really good. The other thing, and I noticed when you were talking about writes and using admission control with that, we have some new enhancements that are coming out in write buffering that are going to be really efficient. And if you think about it, Cockroach has been doing this for a while. I've been here for 6 years, so I've seen the evolution. It's like we've went from having RocksDB, which is at our storage layer, to now Pebble. So we created a more efficient way to store, and we keep optimizing upon that. And then we had the change that you mentioned, Rob, earlier about the Columnar format. That's yet another optimization on it. So we're continuing to iterate on that. So
it only occurred to me about a year ago that Pebble was a kind of nod to the name RocksDB. It only occurred to me about a year ago. I thought, oh, that's a cute name, but I didn't
It's
appreciate the
more efficient. Instead of big rocks, you can have little pebbles and make it
yeah.
more efficient. So anyway, yeah.
So let's look at some best practices. We had a best practices section in our last webinar, but we'd like to look at some different best practices today to give a bit of variety. We'll start with primary key design. And in this example, we're creating the same table, just in different ways. The table stores connection information between graph edges, between two things. So they could be, let's say, LinkedIn connections or Facebook friends, etc. And we'll query the table to say, list a person's connections in descending order of created date. That's to say their most recent connections appear first. And on the left, we have a synthetic primary key and an index on to make the connection, the graph connection, unique. And we also have another index for the query that we're performing. Now, if we ran a query against this table, we would see slower reads because an additional primary key lookup is required to fetch the required data of the query, depending on the query, but also writes would be slower because we have an additional, perhaps unnecessary index in there. On the right, we've adapted the connection, the graph connection, to include both of the connections. So they are inherently unique this time. So that's removed an index. And we've also, this can also be considered a storing or covering index without the use of the storing keyword over the essentially the friend request. So reads and writes in this example are faster. They make more efficient use of columns and everything's a little bit quicker. Happily, if you create the first table or any table for that matter, online schema changes in CockroachDB are entirely online. So you don't have to get it right first time. If you create something like this and it's not working for you in CockroachDB, don't panic. You can make safe online schema changes regardless of the table size without impacting your customers. Glenn, what's the biggest win when it comes to primary key design, in your opinion?
Yeah, I mean, I think this is a great example because it shows two of the things I like to see with primary key design. I like to see with primary keys a good distribution, but also you want the primary key to be where most of your reads are coming from, right? So if you're, I always use the 80-20 rule with that. You know, it's 80% of your read should be coming or more, if you can, coming from the primary key. And having the distribution, you can see in this case, you were generating a key. In the first example, you were generating a key, and that's distributed UUID. But then noticing that the two secondary UUIDs were also being generated probably from a different source that's making the connections, but it still would be in a distributed fashion. So we could take those and make a multi-part key when you're looking up, you know, with both connections and make it more efficient. So I think that's good. So the lessons is don't be shy of a multi-part key if you can get it, as long as it is just really well distributed, because you can lower the number of indexes. Yeah.
And by their nature, UUID, I think we use version 4 UUID in CockroachDB,
yeah.
is uniformly random. So it would result in good distribution across the cluster, which is exactly what you want to avoid hot rows.
Right.
Someone has just asked that they won't be able to watch the session to the. Oh, Alicia is on it. Thank you very much. Okay, so next we're going to look at the differences between upsert and insert into on conflict, and that might be update or do nothing. So insert on update queries always perform a select before updating. So there's always one more query that's involved when you might not necessarily need it. Upsert queries don't require the additional upfront select, but they are slightly less flexible. They only work against the primary key index. So our recommendation would be to use upserts wherever possible, wherever you're inserting or updating something that in a table where it doesn't have secondary indexes. Next, we have row level TTL. And what we're looking at here is a table that every minute, and that's defined by this cron syntax, auto expires anything that's checked out or paid from a user's shopping basket, or anything that is pending or perhaps abandoned after a period of 5 minutes. And what this solves is a bunch of problems. So the abandoned carts in e-commerce examples, but it also handles all of your data retention policies from within your tables themselves. So consider row-level TTL, which also works in the background as an admission controlled job, distributed job, which expires your data without impacting foreground workloads as your tables grow larger.
Yep.
Next, we have column families. Whenever you update a row, you're essentially replacing it with a new one. And by default, all of a row's columns form the same default column family. So everything, if you imagine, without any kind of syntactical sugar, would form part of the same column family. So to save you from having to rewrite large rows where you might not want to update all of the columns in that row, you can use a separate column family. In this example, we have 2 column families. Some of the basic fields that might comprise a member of our database, being the ID and the full name, are in the basics. The name is arbitrary column family, while their image, public key, metadata columns are in a large column family. So whenever the full name, in this case, is updated, we don't have to try to update the image, public key, or metadata fields. So it's a lot faster to do, and there are performance gains. Glenn, do you see column families being used by our customers?
Yeah, I do. I do see column families being used quite a bit. For this use case, definitely to get these large blobs or JSON objects to not have to be replicated. I also see this very common in the situation where customers have it really wide tables, tables, lots of columns, but they're only updating just a few of them. And even if they're not large, blobs, just putting the most updated columns, the columns that are updated most of the time in the column family, can be very, very effective when you have that really wide type situation. So yeah, I do see that quite a bit.
We've had another question. So saying that UUIDs are not that I said that UUIDs are not uniformly random. The version 4 of UUID is uniformly random. There's one byte within there which specifies that this is of type 4, but the rest of the ID is uniformly random. So it's not time-based or anything like that. So you would get uniform distribution from CockroachDB UUIDs. Moving on. Going back to the disallow full table scan setting, in this connection string, the application is passing a disallow full table scans value, and they're setting it to true. So for that session, or any session or connections created for this application, the full table scans would be disallowed. But you can't always control every application that's connecting to your database. And if you don't want full applications running full table scans, you can set it at the role or database level. And if you don't want applications making large scans, there's also a setting for that as well. Glenn, as a rule of thumb, do you recommend that customers disallow full table scans wherever possible? I can anticipate that you would say it depends on workload to workload, but as a rule, is it sensible to disallow full table scans?
It is, but you're right. I would give the engineering answer and say it depends. What I often see with people can have different connection pools, right? Where they can do this. They may have some that won't disallow, like reporting type functions that might need to use that on a much more seldom basis. But yeah.
We've had another question. So if we're going to use primary keys, Upsert is preferable to using insert on conflict. The latter should be used if we want to use columns other than primary key columns. Glenn, do you want to take that one?
Yeah, that's right, and that's typically the case where people have, let's say, a secondary unique index, right? That they want to update. I've seen that used quite a bit. The reason why we use the upserts though is if you use upserts, you can get a fast path right within our environment, and it tends to be a lot more efficient that way. Because again, you're cutting down the reads in half in that case. Um,
So a
yeah,
fast path write is just the write that doesn't incur the preceding select.
correct. Yeah. And I'd also mention if you have too many secondary unique values within the table, you might want to think about the data design, because I've seen some situations where a customer had like 5 or 6 secondary um, unique indexes, multi-part indexes, and we're like, why? That means the
Yeah.
data design wasn't, maybe there should be multiple tables to handle those states. Anyway, so
And they're all going to consume additional data, and they're all going to
correct.
require a write whenever being
Correct.
updated as well, which
Yeah.
has a performance impact.
Yeah. Correct.
Next, we'll take a look at performance in the wild. So first of all, we'll look at a deeper dive on constraints. Now, this is a fairly advanced use case, and I don't think many of our customers are actually harnessing it in the real world. But when starting up a node, you can pass an arbitrary collection of attributes. In the nodes on the left, we're passing an attribute called archive, whilst on the right, we're not passing the attribute. So we're spinning up 3 nodes in this example to store archived data and 3 nodes to store live data. And what this allows us to do is create a partition on the database table so that any data for rows in a purchase table with a status of archived are physically stored and only stored on nodes with the archive constraint or startup attribute. And the reverse is true for rows, without the archive attribute or constraint. So essentially, this allows you to maintain 2 separate. It's all within one logical database, but it allows you to provision nodes differently depending on what you want them to be used for. You might want to have high density storage on these nodes, maybe with slightly slower storage than you would on the hot live cluster of nodes. Now, this is a very extreme example. The difference between 4 vCPUs and 16 vCPUs for a node is quite extreme, as is 100 gigabytes here and 5 terabytes here. But hopefully it gives you an idea as to what's possible by harnessing CockroachDB's constraints. Glenn, I don't know if constraints are widely used by customers, but I was asked a little while ago by a customer if it was possible to separate archive hot and cold data.
Yeah. Yeah. No, they're used some definitely, but I tend to see them used less and less in the distributed environment. But yeah.
Thank you. Okay, moving on. Glenn, do you wanna lead?
Yeah, I'll go through this is kind of my bread and butter that I've been talking about. But basically, um, I was asked to bring forward like some of the most common performance issues, and this is one that I see quite a bit that is luckily easily solved. So explain the scenario when you're looking at the explain plan within Cockroach. You'll see this index join, and on a simple query, you're like, well, I didn't join to another table. Well, we're enforcing this index join because we're using the index to scan some number of rows, but then when the query needs to project the columns out of that, it has to go back to the primary key to look it up. So what ends up happening is you end up doing a lot more reads and reads across the network. So you scan this index to get the values that fit the criteria, and then you go all over the cluster to actually find little bits of information to make the full answer. So next slide. Yeah.
Would this be the words read amplification nicely describe what would be happening in this scenario, or is that something separate?
That can be something separate, but you could say that, yeah, absolutely, because it really is amplifying the number of reads to get the same answer, essentially. So yeah, so you can see what's happening in this case. So where the very easy solution is to use the storing clause to store extra values in the index, such that you can scan and do essentially one read. Instead of, like, you see this case, this example, I'm doing a scan, and you see at the very bottom where it says limit 100, I'm scanning 100 rows, and essentially with read ahead and everything, that's going to be one, maybe two reads on that index, right? And then, but then it has to go out to all 100 additional reads. So with one read, I can, instead of 101 reads, I can fill that if I use the storing clause. Next slide. Yeah.
So that's actually an
It's a
order of
huge,
magnitude potentially
yeah,
faster.
yeah, huge amount, and you'll see in the coming slides that this is what it looks like essentially. I have, this is my example that in the previous slide where, you know, essentially just have two different keys that I'm searching from. And this is what the queries look like, where I'm limiting to 100 by order. Anyway, next slide. Yeah.
And I suppose you could probably run this kind of workload. I know some of our customers do
Mm-hmm.
in a blue-green canary fashion, whereby you can make one of the indexes hidden or not visible,
Oh,
I think is the
sure.
syntax, and that will instruct CockroachDB's cost-based optimizer to not or to never use that index. So you could perhaps play around with indexes to find the best index without having to make lots of schema changes.
As a matter of fact, I use that quite a bit at customers because sometimes we'll want to introduce a new index, but people are worried that there might be some query that could be relying on it somewhere else. So we'll introduce the new one, make the old one invisible. But if there's a problem, you can revert back really quickly because it's just a, you know, metadata update. Yeah, thanks
And
for bringing that up.
customers running enormous tables are applying this as well, so it's safe.
Right.
I'm guessing at any scale.
Yep. Absolutely. Yeah, and so here's some of the performance improvements. This one was done on some tests that I was using to show the difference, but massive increase with in performance with less CPU. I mean that's the key point. People that want, you can see how the CPU in the first case, this is running it with and without, you know, with index join and without index join. You can see where it's very distributed, and it's not you know, clustered together very well. But in the case where I'm using the storing clause, I'm able to use way less overall CPU and get way more throughput.
Yeah, and it looks generally more reliable from a performance
Right.
metric. Everything's tighter
Yeah.
together, whereas everything's very much spread
Right.
out over here.
Yeah.
And if you were to have an unexpected spike and it was to affect this node here,
Yeah, you're basically done at that
yeah,
point. You're basically
yeah.
done. Yeah.
I think that's
And
incredible that you can get better performance for less CPU, which
yeah.
might, in this case, the customer might be happy with the additional headroom, but they
Oh,
also might want to lower reduce the size of their
cost.
nodes. Yeah, absolutely.
Yeah, the cost to serve. Yeah, and the next slide is actually some real life examples of where I did this in the wild,
So
as
this
you
is a
say.
customer cluster we're looking at
Yeah,
here.
yeah. So basically, we're using 50%. We have all these spikes, and you can see that's the CPU percentage, and you can see below in that same slide are the metrics, the statements, and the statements are coming in at the same level, but then um, you can see the latency dropping dramatically,
Massively.
massively on the left, and the same with the one on the right too. Yet another scenario where I'm going along, and then I just make that one change to the proper index, and I go from essentially average of 12 milliseconds down to about 3 milliseconds. So
For much lower CPU.
Yeah. Yep.
Yeah.
So anyway.
We've had 3 questions in the time that you've been speaking, Glenn. So I'll get to those in
Sure.
the order that they arrived. Glenn, are you looking at the Q&A section as well? Can you see these questions?
Yes, I can. Yeah.
Would you mind tackling the first one?
Yeah.
When we have a composite primary key, that one.
Yeah. The composite
Thank you.
primary key. Yeah. Thanks for the question. Yeah. We have a composite primary key. Essentially, yes, with Cockroach, all the values are sorted by those composite values. So if you do have the first, key one, key two as part of your filtering criteria, in the where clause, then absolutely you don't need another index for those two values. So that's a good one. But if you were searching just by key three, you would then need an index. But yeah, so the ordering does matter quite a bit.
Thank you.
Yeah,
We've had another question. Which version of CockroachDB supports constraints? And constraints are actually nothing new. They go way back in the product, and they're what allow us
yeah,
to do a lot of cleverness under the hood with geo partitioning and node locality, etc. So nothing new there. It's been in the product for a very long time. The next question is, do we have a CLI or software tool that we can use to run against clusters and databases to report inefficient SQL queries? Yes, we do. We have a CLI. If you run a query with explain, it will tell you if that query is inefficient, and it will suggest indexes to create on that table. So it won't necessarily, I would obviously benchmark the suggestions that it's coming at as opposed to blindly copy pasting what it suggests, but it will surface them up. And there's also a user interface where you'll see the same kind of insight and workload recommendations. So yes, and in a very soon to be released product in the cloud, we'll also show you metrics that go down to the low level of individual SQL queries and how efficiently they're running.
yeah. The other thing I'd add about that, Rob,
Mm.
is within the DB console, we also have um, we show these queries and give insights to the individual queries as well. So and that can be really useful for a customer.
Yeah. Glenn, do you want to take the next one? So the question is, when there are small read mostly tables, for example, code tables, I'm guessing reference data, things like that, that are heavily used in joins with large tables, is there any caching or other optimizations that minimize movement of small table data between nodes?
Yeah, essentially, with that, essentially each node will cache the values that are looked up. So essentially, you can and within Cockroach, it's interesting. We do that automatically, so you really don't have to worry about it too much. I remember back in the days at Oracle, I would always worry about setting tables to cache mode and things of that nature to keep them from running out of the cache, but it's done pretty much automatically. You could use, if you had a multi-region environment, you could use what's called global tables, and then you could make the global tables, especially if it's a small lookup type table, be cached or be in each region essentially, and that can be really, really effective for environments where you're joining to this, lookup table quite a bit. Yeah.
Similarly, for and potentially in conjunction with, but not necessarily, follower reads are also hugely
Correct.
beneficial in the movement of data in order to access it. For example, if
Correct.
you hit a node that is a replica of a piece of data you're looking for, but not necessarily the leaseholder, if you're using follower reads, the data can be served and it might be slightly stale. We're talking perhaps in the order of 4.5 average seconds, but that's also another option for you. And that will speed up your queries if you can tolerate ever so slightly stale data. And especially
Yeah.
if you're looking at reference data that rarely changes.
Yeah, and I've seen customers in single region use that. I've seen customers in single region, let's say they had a 9-node cluster, pushed a 9-node replication for that one table, and then use follow reads, and then everyone's going to be local. That's depending where you come
Wow,
in. Yeah,
that's a great idea. I'd never
it's an
considered that before.
optimization. Yeah.
Yeah. And the last question I see here is it's a spicy one. If performance is the only concern, why not just run a single instance of Postgres? I think that's a very sensible question. If performance is your only concern and you're not worried about resilience or anything like that, running on a single node will always, at least for a point lookup query, be faster than running on a distributed SQL database because there are no network hops involved. However, you'll quickly reach the ceiling of what that single node instance is able to provide you in terms of throughput and scale. You'll never reach the resilience or total throughput capabilities of a distributed SQL database. There will be millisecond latencies in a distributed SQL database, whereas you might get single digit millisecond latencies or perhaps late microsecond latencies with a single instance. It really depends on your workloads. CockroachDB for mission critical workloads will offer you a much better user experience in terms of resilience than a single node any other database would be able to provide, because those kinds of databases weren't necessarily developed with the resilience requirements of today, thinking about DORA, etc., or the geographic nature of modern day applications in mind. Good question. So we reach the last couple of slides and we'll go through some key takeaways. So I'd like to recap that database performance is a science, but it's not rocket science. There'll always be a solution to the challenges or performance bottlenecks that you're facing in a distributed SQL database. And we've achieved some big performance wins since our last performance webinar that was a year ago. So no matter how complex your schemas or databases, you will enjoy good, solid performance thanks to CockroachDB's flexibility. There are 2 QR codes on this screen. One is on our Get Started. So if you want to learn more about CockroachDB, that's a good QR code to scan. And if you'd like to watch some YouTube videos that dive a little bit deeper into some of the performance topics here that we've covered today, or a wealth of other topics that we haven't covered here today, that's a good QR code for you to try. There's a special takeaway, and I'm noticing the Q&A questions, so don't worry, we'll get to those. And there's another special takeaway. We've recently released the 2nd edition of our definitive guide book, and there's a free PDF copy available to you. Just scan the book link there, and that will take you to the website where you'll be able to download the PDF free of charge. So let's go to Q&A. Before we do, I'd like to thank everyone so much for attending. We've had a really solid turnout. The questions have been flowing, which has been really good. We will provide contact information. We will have your contact information for follow-up. We would love to see you at future events. And yeah, let's carry on. So we've answered that one. Answer live. Okay. So let's say we have 4 tables with regional by row data domiciling. We have table 1, 2, 3, and 4, and all 4 tables share a common column, say order ID. Is there any possibility to co-locate the records in the same node of all 4 tables having same value automatically without using predefined partition? Glenn, do you want to take this? Because I think you probably have more real world experience than I do.
No.
I mean, what I could probably add is basically, if you are geo-partitioning data and it's within the same region, worst case scenario, you're going to be housing similar tables in the same or adjoining availability zones. So we're still looking at very low millisecond latencies.
Right. Yeah.
But depending on your replication factor, let's say your region houses 3 nodes for sake of argument, and you've got a replication factor of 3 and you're domiciling data to that region, each of those nodes is going to have table data for all 4 of those tables. Anything you want to add to that, Glenn?
No, that's right.
Cool. Next question. Oh, I see. The main intention was to avoid distributed joins. Yep. Yeah. And as an aside, now that I know that was the meaning for the question, you can also run an explain, as you may already know. If you do an explain distributed SQL in brackets, dist SQL, it will show you a visual representation of your query. So that's available from the CockroachDB CLI. So definitely something to play with if you're running a multi-node CockroachDB cluster. Next question. Can you describe in brief what the mechanism looks like if you want to upgrade from basic to standard to dedicated? Sure. So basic to standard is available via the cloud API at the moment, but very soon will be available. I think it actually might be in preview at the moment in the UI. So there's a drop down for your cluster in actions, and you can simply upgrade from basic to standard and actually back again, depending on your workload requirements. The upgrade path from standard to advanced, as it's now called, is in the pipeline. So too is the migration path from advanced to standard, which I think may be a little bit ahead of that. Next question. What are the most common performance issues that CockroachDB customers run into? Now, Glenn, I'm going to definitely pass this one over to you because you are the expert on this.
Yeah, I mean, you saw it in the slides. Essentially, that is the most common issue where
so indexes.
They'll use indexes and not have the index set up properly. They're doing this index scans and then having to join back to the primary key. That's one of the largest one. But thinking about what that what that means is basically what you want to do with Cockroach is you want to keep things as local as possible. So whatever that means, right? Whether it's in multi-regions by pinning things, partitioning things properly within the indexes to make sure that you don't have to span out to multiple nodes to answer the question. That's key. The other one is also keeping it local, but also keeping your transactions to a reasonable size too. Doing huge bulk updates to multiple rows is not a good practice either, because then you end up, going out to multiple nodes and having to lock over networks. So that tends to be those two areas when it comes to large transactions and non-local access is what tends to be where I focus really most of my performance tuning efforts.
Yeah. Being very mindful of everyone's time. I don't have a hard stop, and some of you may not. We will get to as many questions as we can, but appreciate that some people might have to drop. So to anyone who has to drop now, thank you very much. If we have a couple of extra minutes, Alicia, I'd like to continue just to try and tackle some of these questions, but we won't be able to tackle any more than we've already received. So what are the most common... Oh, we've done that one. There we go. Does CockroachDB plan to support native UUID v7 generation? I honestly don't know the answer to that question.
Yeah.
I'm afraid. I can do some digging, and if I find an answer to that, I will.
Yeah, I know engineering is looking, but I don't know. Yeah.
So the answer is yes. We're looking into it. Potentially. Next question. Can global tables be used where there are in some heavy write scenarios, such as in batch jobs? I wouldn't necessarily recommend global tables for heavy write scenarios. Global tables incur higher write latencies because the data needs to be replicated to more potentially geographically dispersed nodes in order to provide lower latency writes for global users. So perhaps global tables for a write heavy table isn't necessarily the best topology pattern to use. Would you agree, Glenn?
Yes. Now, if you had to do it once in a while, that's okay. But
for a heavy write workload, perhaps not so much.
Yeah.
Okay. For bare metal deployments, are there any CockroachDB specific recommendations regarding operating system settings, especially regarding thread counts, CPUs, and connections? We do have recommendations for this, and if you Google CockroachDB production checklist, you'll find a bunch of recommendations from us, and we keep that up to date as we learn more about the product from our customers and ourselves.
We also have some customer run books for that too, so you could take a look at that. Yeah.
Perfect. If you could share a link with that, perhaps after the fact, that'd be really useful. Thank you. And finally, do we have a scope for introducing interval partitions for distributed requirements? I'm going to have to defer to you, Glenn, because I don't know what interval partitions are.
I don't know if that's being looked at or not. To be honest, I'll have to get back to you. Yeah.
Well, that's all of our questions and all the time we have today. Thank you, everyone, so much for joining us. Please fill out the survey so that we can make any future webinars better, and we'll hope to see you soon. Enjoy the rest of your days.